Welcome to another Fibre Laser Learning Lab. Here we've got some D-grade colours. Yeah, I know I said I was never going to go back and do any more colour chasing, and we're not. Now I owe these colours one thing, and that's a big thank you. Although I am very disparaging about them and the quality of them and the durability of them and the time they take, they have taught me a great deal about the parameters that are used to obtain these colours, and they've given me a great understanding of exactly what the parameters do on this machine. Now, although we've tackled parameters in various ways in different sessions up to now, they have been independently looked at without trying to work out what the relationship between them is. So today I want to look at all these parameters separately in a slightly more in-depth way than we looked at before, but I also want to try and demonstrate the relationship between them. Now, individually, these are all separate parameters, but I'm afraid you can't just adjust one of these parameters and expect it to, if you like, move proportionately, because some of these parameters, as you change one parameter, it changes some of the other parameters. And that's the interrelationship which I want to look at today, and the lesson that these D-grade colours have taught me. Now, percent power is a fairly blunt tool, and you may think that changing the power by 50% reduces the damage to the surface by 50%. Wrong. Because other things are happening when you change percent power as well as the watts. Let's try and tease that apart and explain to you, because I hope that the pictures that I'm going to show you today will give you a much clearer image that you can carry in your mind when you're adjusting these parameters. Now, the whole point about these D-grade colours is that they are not interfering with the texture of the surface. They're only interfering with the thickness of the oxide film on the surface of the material, and that oxide film is only a few nanometers thick. So by definition, we don't need huge amounts of heat and energy into the surface of the material to modify this oxide layer. So the whole point about these colours is it requires tremendous finesse and control of the parameters to manipulate the oxide film. Now, JPT in their specification claim that they've got a 7mm diameter beam. Now, I don't know exactly what that means, but let's assume that it means what I've drawn here, that we've got a beam which is 7mm in diameter total. It's claimed that there is a very near Gaussian distribution power within the beam. And so here we've got a graph of the light intensity within the beam itself, which follows this Gaussian distribution. So we've got maximum light intensity right at the centre of the core of the beam. This central third of the beam is carrying about 70% of the light intensity on average. I mean, obviously the intensity in this area changes as well, but there's 70% of the light intensity which could be interpreted as power or energy or destructiveness is happening within the central section of the beam. Then there's about another 27%, I think it is, around this next section, and about 5% at the outside. So we're taking a 7mm beam and we're going to put it through a lens which is 254mm focal length. Now that's quite a long focal length lens, but once it gets down to the focal point, it focuses down to something called a spot size, which is 0.07. Now, I think in reality it's 0.065, but for convenience purposes, as you'll see in a few seconds, I'm choosing to use a near equivalent 0.07. Because 0.07 happens to be 100 times smaller than 7mm. So what this means is, as I push this 7mm beam through a 0.07mm spot size, what happens to this normal distribution? Aha! It's still a normal distribution, even at the focal point. I've drawn this normal distribution here, and I've called this height of the graph 100% power. It doesn't matter what the height is, I'm just nominally calling that 100% power. So if I take this 7mm beam and compress it down to 0.07, effectively what I've done, I've amplified the light intensity within this graph by a factor of 100. If I look at what happens here, when I multiply 0 by 100, I'm still going to get 0. If I multiply these very small low intensity values by 100, they're still going to be low. But as I move up this graph here and I take this high value intensity and I multiply it by 100, I'm going to get something which is very interesting. We're certainly not going to get this same normal distribution shape at the focal point. What we're going to get is this. Now I've drawn this baseline here away from the focal point just for clarity, but look, you can just see very small there the normal distribution curve that I've drawn. Well, that's not what's going to happen. This is what's going to happen at that point. We're going to multiply the intensity of the light by a factor of 100. As I said to you before, 0 multiplied by 100 is still 0, and so this baseline will still be the same across here. But what will happen is to the rest of the curve, it's going to expand in a very disproportionate way. And effectively what we've got here is a very sharp point of energy. Now, I do not want you to run away with the idea that this is a real thing, like a drill. It is a graph of the light intensity within the beam. And remember, light intensity is damage. The more intense, the more the damage. Understanding this is not a drill, but a graph of energy intensity, and it's got a very, very, very sharp spike of energy at the center, as you can see there. And that spike of energy remains pretty sharp for quite a long way back before it starts, let's call this softening, shall we? As the light intensity gets lower, so its ability to do damage gets less. So that's what happens at 100% power. And for comparison, let's take a look at 50%, 20% and 10% power. Now, as we multiply that normal distribution by these numbers, here's what happens to the graph of intensity. As you see, it's getting shorter and shorter. But the one thing that you can't really see is that not only is it getting shorter, but this point here at the end is getting softer. It's becoming much closer to this sort of shape. Here, look, we've got a huge range over which we've got very intense light and damage can be done. Here, the range has dropped down quite considerably, and here it's even less, and here it's probably non-existent. Effectively, this shape is containing 20 watts. Now this shape here is containing 10 watts, and this shape here is containing 4 watts, and this shape here is containing 2 watts. Even though the power in total has dropped off, the way in which the power is being applied to the surface is changing as well. It isn't just power. We've got sharp power and we've got blunt power. That's the best way that I can describe it and the best way that you can visualize it. The power is being applied very softly and gently here, but here it's a bit brutal, a bit sharp, a bit spiky, exactly like the picture looks. But I must insist, you do not imagine this to be a drill. This is not something solid. This is just a graph of intensity. Okay, now you will start to hear me using the term sharp and soft. I'm talking in terms of the way in which energy is applied gently to the surface or in a very sharp manner. And I suppose the other way that you could imagine what I'm talking about when I say sharp and soft is this. A sharp beam will produce damage to the surface like this, where we shall have quite a deep hole in the middle and a little bit of a softer hole around the outside. But here, look, here's the shape of the pit that will be made by a sharp beam. Whereas when we get to the other end, we can have the same diameter, but the damage to the surface will be much more uniform and gentle, and it won't be aggressive like this. So that's the other way that you can imagine soft and sharp. In all MOPA lasers, there are a selection of pulse widths that you can choose. That's what makes this different to a Q-switch laser, where you only have one pulse shape that you can generate. You can vary the number of pulses and you can vary the power in the pulse, but you can't vary its shape. This system here, with its 16 different pulses, allows us to have great finesse over the amount of power that we put down onto a surface. Now these are just a pictorial representation of all the pulses that are available. You can see we've got the very shortest pulse here, which is a 2 nanosecond pulse, and then we've got the longest pulse here, which is a 350 nanosecond pulse. Nanoseconds are a billionth of a second, so you know they're not very long pulses, even the longest pulse. But the most important thing about them is this bit here, the rise time. It's a very, very rapid rise time to get to its, let's call it peak power. I mean, the peak power for a very long pulse is still about 6 kilowatts. And the peak power for these shorter ones is up here in the 12 to 13 kilowatts, right at the top here. So they've got a very sharp, very powerful pulse. Now the one thing that these fibre lasers at 20 watts can do that you certainly couldn't do with a 20 watt continuous power CO2 laser is to damage metal. And there's a very fundamental reason for that. You may remember a couple of sessions ago when I demonstrated the crystal structure or the atomic structure of various materials. There were different stiffnesses because of the bonding arrangement between the molecules and the atoms. Now, with all metals in their solid state, they have got a very crystalline, uniform structure. And that crystalline, uniform structure is very, very difficult to oscillate and vibrate with photons. So it's very difficult to get heat into metal with light, because most metals are in the 96 to 98% reflective. That means you're only able to push 2 to 4% of energy into the material, which means you've got to pump a hell of a lot of energy into the material very quickly to change it from solid to molten before it gets a chance to realize what's happened. Now, once the material is molten, you have actually destroyed the uniform crystal structure, and it will absorb the energy and continue to melt. That's why I mention this rise time here. It's a very rapid rise time, and not only is it a very rapid rise time, but look, we're talking about kilowatts from a 20 watt laser. So the pulse that we're stimulating the material with is extremely energetic. And I'm absolutely sure this is the reason why you can damage metal with this laser that you can't do with a 20 watt continuous beam laser. So the rise time on a CO2 laser is about a millisecond, whereas the rise time on this beam is in the order of a nanosecond. Let's take a look at one of these pulses, and the one that crops up and gives the widest range of this colour that we're looking at on here is down at the bottom end here as a very sharp pulse at 4 nanoseconds, that green one there. Peak power on that is somewhere in the region of about 12 kilowatts. And to do that, you have to run the system at 500 kilohertz. If you run it at other than that, you won't get 12 kilowatts. Now, depending on how good your memory is, you might remember seeing that picture or something similar to it in one of the early sessions when we talked about how this fibre laser works. Now, the scale across the bottom is the pulse repetition frequency, or the kilohertz, and that runs between 0 and 1000 kilohertz. The pulse that we want to look at is halfway across here at 500 kilohertz. So that's where our 4 nanosecond pulse is. So at the start of a new cycle, the pump diode will switch on and gradually increase its intensity, which its ability to convert electrons up to their higher state, and eventually we shall reach this point here where the charge will then be released and we will get our 4 nanosecond pulse. If we choose a frequency higher than the 500 peak value, then what happens is the power will still be available there. We will still have 12 kilowatts available to us, but what will happen is that 12 kilowatts will drop off in a non-linear way as we get towards 1000 kilohertz. I mean, right down at this end here where it's roughly 200, we've got about a 13 nanosecond pulse. So we're still talking about that pulse there, which is still not a very long pulse. But what happens is we could strangle that pulse before it even gets up to power. By, for instance, we could decide to run it at 100 kilohertz as opposed to 200 kilohertz. Now 200 kilohertz will be peak power and 100 kilohertz will be approximately half power, because it will be halfway up this linear charging. So we have got the opportunity of playing with the power within the pulse by messing with the pulse repetition frequency. Now, if you do it on the upside while it's charging, it's fairly linear. If you do it on the downside, where you've got a lot more pulses to work with, you've still got the same amount of power, but you've got to divide that power over many, many more pulses. So as we start going along this non-linear scale here, we're actually producing a non-linear rise in the power within this beam. So right up here at, say, 800 kilohertz, we've only got a very small amount of energy that we've put into the beam. So that's what we're going to get out. Now, the reason I need to point that out to you is although you think you're working down this side of the beam, in reality, you're still only charging up on a basic linear charge, but you're selecting points along that linear charge which are non-linear because of this graph here. We've got a relatively sharp beam here, but as we start attenuating that by messing around with this frequency along the bottom here, it will no longer be a 13 nanosecond pulse with a sharp peak. What will happen is it will still be 13 nanoseconds wide, but it will start coming down here and becoming softer and softer. So the more you attenuate it, the more you soften it. And remember, softening does less damage. Here we can do a lot of damage into the material, but in a very short period of time. Here we'll do a lot of damage into the material over a longer period of time because we've got some sustain on there. So we shall actually be able to do more damage with a 13 nanosecond pulse than we will with a 2 nanosecond pulse. But if you soften a 2 nanosecond pulse, even right down here, it's still going to be pretty sharp. Whereas with a 13 nanosecond pulse, as you can see, it's going to get softer and softer. I hope I'm showing you this strange relationship between pulse width and softness as you start attenuating it away from its peak value. I keep coming back to this because we need soft power to heat the few nanometers of film, because we don't want to break through the film. If we want to break through the film, then we need sharp peaks. We need lots of 100% power and sharp points, regardless of which one we choose. I know these are already soft, but you can soften them even more by, first of all, attenuating the power by not using the specified peak power frequency, and you can soften them even more by messing around with the percentage power. So you can put softening on top of softening, or you can put sharpening on top of sharpening. Now, I know these are very strange terms I'm using here, but I hope they're sufficiently diagrammatic and pictorial for you to carry in your brain and help you to try and understand what you're doing when you're messing around with these parameters. So there's three features here that you can mess around with to decide whether you want a puddle or a pothole. Power, which is a very, very blunt instrument, but you can superimpose that on the top of the pulse choice and the frequency that you use with your pulse choice. So we can strike off percent power, we can strike off pulse width. We haven't talked about pulse repetition frequency completely, because pulse repetition frequency is also linked to speed. Let's take a look at that relationship, should we? We've seen the relationship between pulse repetition frequency, pulse width and power, because there is a link between those, but there's a second link here and here. Now, I've drawn this picture for you before, but we'll draw it again and try and explain it again. For a 2 nanosecond pulse, the pulse repetition frequency is 850 kilohertz. Now, let's not get too picky about that. Let's call that 1000 kilohertz, which is basically 1,000,000 cycles a second. So we've got all this time when nothing is happening. Hey, yeah, I'm some sort of comedian. Look, 1,000,000th of a second, all this time. We're looking at things in relative terms here. So 2 nanoseconds, and this is 1,000,000th of a second, or 1,000 nanoseconds. Now, I'm not going to get another one of these pulses until here. So we've got all this time in between when nothing is happening except cooling, because this is heating and this, all of this is cooling. On that basis, we're not going to heat the material up at all, because we've got 998 nanoseconds of cooling and 2 nanoseconds of heating. Well, that's ridiculous, isn't it? The only saving grace is the thermal conductivity of the material is just not going to respond quick enough to drag the heat away in this short period of time. So, yeah, there is a little bit of physics which will work for us in this case, and my exaggerated cooling is not quite as exaggerated as I'm making it. But what we've got here is 1 microsecond between the pulses. I've made life easy for myself. I haven't covered all the combinations, but I've covered the basic 16 pulse widths that we've got there. And what I've looked at is that for a 2 nanosecond pulse, operating at its proper 850 nanosecond period, if we run at 1 millimetre a second, we shall put down 850,000 pulses in that 1 millimetre, because 1 millimetre a second, 850,000 pulses a second, because that's what this says. So if we raise the speed to 100 millimetres a second, we're going to get 8,500 pulses per millimetre. That's still a lot of pulses per millimetre. And if we increase the speed even more, up to a maximum of 2,000, which is what the machine can do, we drop that down to 425 pulses per millimetre. So what, I hear you ask? This is 850 kilohertz, remember. I'm going to give you a very silly example now of 1000 hertz. Not 1000 kilohertz, but 1000 hertz. 1 millimeter over 1 second, so I'm travelling at 1 millimeter a second. I'm going to produce at 1000 hertz, I'm going to put 1000 pulses down in 1 millimeter, and that's what it looks like. That's at 1000 hertz. Now at 1000 kilohertz, I'm going to get 1000 times more pulses in the same distance, in the same time. So in terms of heating, there's a relationship between speed and pulse repetition frequency. But of course, pulse repetition frequency that I've shown you just here is just the maximum pulse repetition frequency. You start adding that in to varying the pulse repetition frequency with the pulse width. And you've got all sorts of combinations that can happen now. So we've got this one, which is linked into speed. And then you can add power to it as well. So you can change with 4 of these variables playing in together. And then we've got this thing here, pitch, which is the spacing between the lines that you're scanning. Now here I've got just a simple example of the 0.07 beam moving half a beam width. 0.035, 35 microns. Most of these on here are around about 1 or 2 microns. Just imagine the overlap that we've got when we do all these pulses all this close together. So we've got a tremendous heating effect that is potentially there. But what do? Well, we can kill it with speed, we can kill it with power, we can't kill it with pulse width because we've got a fixed pulse width for our test, but we can kill it with pulse repetition frequency. So we've fixed the pulse width because we said that most of these are all done with a 4 nanosecond pulse. That's the only thing that was constant throughout all of those tests. Now with this line here we changed the pitch between the lines. This one here we changed the pulse repetition frequency. This one we changed the speed, this one we changed the power. Now, I will explain to you in a few seconds what we did to get these results. But just to show you that there is a big difference in manipulating the power with each one of these different parameters. Now, this is not mixing the parameters. This is just keeping them plainly one parameter at a time. All the others are fixed and constant. We did talk about in a previous session focus. I mean, this is about 0.5 thick stainless steel. Here's our material base. Let's call that, as far as the machine setting is concerned, that's classed as 0. That's the table. Okay, now when you go into EzeCAD, you can offset for your material thickness, and my material thickness is 0.5. EzeCAD will not allow me to decrease the material to less than 0. It will only go plus. Okay, so the very worst I can do is to push my focus down to the table, which is minus 0.5. Now I'm told that that is allowable. Let's just come back to a second to this picture here. Now, as I tried to explain to you, this is not a drill. This is a graph of light intensity. But what that does mean is to say that the intensity at this point is not uniform. Therefore, when you've got 100% power, you can do damage maybe 8 or 10 millimeters below the focal point. And equally well, because this is a mirror image inside here, as the beam squashes down, you will equally well be able to do damage 8 or 10 millimeters above the focal point. I'm told that you mustn't ever go, the way that I'm going, below the focal point. I'm trying to get to the bottom of just why I can't defocus. I'm told that it's all to do with reflections back into the laser. I can't explain it to you at the moment because I have got no idea why or how it happens or it can happen. I'm trying to get an explanation, and when I do get an explanation, I will point it out to you guys. But in the meantime, I've got to pass on the warning that I've been given. Don't go below the focal point. Always raise the material up. Okay, that said, let's just see what this means. We've got 10 millimeters plus or minus here, maybe, if you're using full power. If you start reducing it to 50% power, then what happens is the focal point, or the point at which you cease to do damage, gets closer and closer and closer to the real focal point, which is there. If you're using low power, you might be able to use a little bit of focus to attenuate the power even more. If you've got 100% power, you've got to move a long way, plus and minus, to get any effect of this end of the peak. So although you can mess with focus, it's very much a bit of a variable because you don't know where it is, because it depends very much on your percent power. So in general terms, I would say don't mess with the focus. You've got enough control with these other features. So what we're going to take a look at now is the way in which these features affect colour. Because remember, colour only happens under a certain set of conditions. You start moving away from those conditions, and I cannot tell you exactly what those conditions are. We are working in this region here, the puddle region. We want everything soft to produce these colours. We mustn't damage and get through the chromium oxide film. So everything that you're going to see here is associated with this end, the soft end of the power region. Now all these tests started off with exactly the same parameter for like a magenta colour, a D-grade magenta. Now I've got these being viewed at a very low angle to the light so that you can see them. But what I'll now do is line up the parameters here for you. Now you can probably just about see that one on the end there, which is 21%. That is virtually invisible. But when you catch it in the light, it produces these iridescent colours like you see on a bubble. Then we move on to these oranges, and then through sort of a pale mauve. This one here, A1, which is 23% power, is the standard that we shall use throughout. So we've managed to go from 23% down to 21% before we lost it. And we lost it actually at 22%, so we were fairly close to the band where we could lose red. As we came up the scale here and increased the power, 24, 25, 30, 50, 70, 90 and even 100%, we've gone to a very dark blue, as you can see here. It's a navy almost. And here's our standard again in the middle, which is the same as that one. And as we increase the speed, effectively what we're doing is decreasing the power, because we're putting down less dots per unit of distance, less dots per millimetre. What we've then found is that we can actually stretch this colour, this orange, through quite a few more steps by changing the speed than we could by changing the power. By changing the power, it just dropped off the end of the scale here. It was 21%, whereas here we're able to go down in much smaller increments and follow the colour down. So as we start going up the scale, we're going up in bigger increments now, 750, 700, 600, 500, 400, 300. When I say going up, what happens is the power is going up as the speed is going down. We're putting more dots per millimetre down. So we're putting more heat into the material. And we're getting commonality sort of here, but then when it drops off beyond this point here, these colours, we don't drop off to pale mauve and then dark mauve. We go through this dark mauve and then we get through to green, very dark green, and this looks like a very drab olive. So it looks as though we've got more control over the heat application, if we want to regard that as what the term is, by changing the speed. we've got constant power, we've got constant everything else. The pulse is constant at 4 nanoseconds. So if you like, the shape of the puddle is exactly the same. The only thing that we're doing is changing in this instance, we are changing the shape of the puddle by making the puddle softer and softer. Here, we're increasing the distance between the puddles. And I'm using these crude terms, which I've tried to associate with pictures, so that you can try and understand that these are not doing the same thing. Although they're changing the power, they're not changing the application of that power in the same way. So now we're going for the pulse repetition frequency. Now the maximum power is achieved at 500 kilohertz. And so what we're now doing, we're softening the power by going to 480, 460, and at 440 we've softened it so much that it's dropped off the end of the scale. And then you can probably just about see that one. That's 600. So we've dropped off the end of the scale again. And as you would expect with pulse repetition frequency, whether we go up or whether we come down makes no difference. We're going to get a reduction of power and a softening of the peak. And that's exactly what we can see here. Basically the center is correct and then it's dropping off either side. So with everything else constant again, here's our standard, which is the same color to start with. And now as we basically, what we're doing this way, we're going 1.7, 1.6, 1.4 and 1.0 micron pitch. We're getting closer together. Now that means as we're getting closer together, we're applying more power per square area. And as we apply more power per square area, we're moving through purple into a dark purple or a mauve. And effectively, it's achieving the same sort of result to a certain extent as when we're increasing the power here. Okay, and we're doing something similar when we increase the power here by decreasing the speed. But it's happening probably quite quickly here. 1.7, so from 1.8 to 1 millimetre, 8 microns, produces quite a significant change of colour. Now when we come the other way up to 2 microns, and now we're decreasing the power because we're going from 1.8 to 2.8, and at 2.8 we've virtually lost it again. We've gone through these oranges to something which is a very nice iridescent bubble, clear colour almost, and we get that effect again when we decrease the power here and here, and we've decreased the power here, and we've gone through this series of oranges here, but we didn't go through oranges this way. We did touch on an orange that way as we disappeared off the end. We touched on oranges and we disappeared out these ends of the range, and we got to an iridescent colour just there. Now as you've seen, there is some vague similarity between these results. When you decrease the power you tend towards orange, and when you increase the power you tend towards mauve and eventually green or very, very dark blue. That's about where the similarity ends, because you start mixing these and the results are very unpredictable. Now before we adjourn to the workshop, here's what I'm going to try and do. We've started off with 4 colours in here, one off of each of these charts, and they're all at the low end of the power. So here we had percent power, and we went down to start with from our nominal colour. We went down and disappeared off the end of the chart before we pushed the power up. So A2, which is that one, is low power orange. So we increased the speed to start with, and as we increased the speed, so we're reducing the power, and here we are at B4 with orange again. And then with the C range we were playing with the kilohertz, and whether we went up the chart or down the chart really didn't matter. We could have gone for either C6 or C10, and I went for C10, both of which are decreasing power. then we went finally for pitch. As you close the lines up, the heat intensity increases. And then as we open the pitch up, we start getting cooler, less heating per unit area. So here we've got a D8, which is that one, which is an orange. All of the oranges represent the low end of the power range. They're totally different textures, even though they look like the same colour to the eye. So the power that's being applied to the surface is completely different for each one of these parameters. The whole point of my exercise with these colours is trying to make them more efficient in terms of cycle time. And the way that you make them more efficient in cycle time is to open up the pitch as much as possible. So can I get back from a high pitch, and trust me, 2.6 microns is still not a very high pitch, but it's still better than the 1.8 that we started with just here. Can I drag that 2.6 orange back towards this colour by attempting to move some of these other features? At 2.6 microns, I've cooled the job down because I've opened up the pitch. So therefore, the strategy is to try and heat the material back up again by changing some of these other features. Now, if we decrease the speed, we're going to put more heat into the job. Or we could increase the power. We could increase the power and decrease the speed. We can't really do anything with C4. We're already on the most efficient PRF, maximum power, for this colour. So if we catch those in the light right, there's our orangey gold that we're starting with on the bottom. And there is our target colour that we're aiming for, which is the magenta-y colour at the top. So we're trying to move up this chart here towards that target colour. Now we can do it by coming down this chart or this one. I think the first thing we'll try is we'll come down here from orange, and we've only got to take a couple of steps and we should be back here at the correct colour. And we've done that by changing the power by just 1%. So currently the power is 23%, and we've got to increase the power to get a little bit more heat into the job. So if we take it from 23 to 24%, that should fix it. Well, as you can see, the good news is we're going in the right direction, but we haven't got there yet with 1%. We've got to a pink rather than a crimson or a magenta. So let's go up another 1%. Will that get us there? Well, it's getting closer, but it's still not a match. As you can see, we've got two pinks that are the same almost. Let's go another percent. I think you'll see that there's no difference in the shade of those pinks. So we go from 26 to 36% power. Now remember, what we're doing is we're increasing the power, we're making the pulse sharper. We've not changed anything else, we've still got our soft everything else. So increasing the power started to take us in the right direction, but then started carrying us off in a completely different direction, because now we got three pinks that were more or less the same, but now we've got a pink here which you can't see it unless I turn it round. And now as I turn it round, look what's happened to my pinks. They've disappeared. But what about the one on the end that I've just produced? As I pointed out to you as I was doing it, we've increased the power, we've made it sharper, we've worked our way through the surface of the material now, and what we've done, we've produced a B grade colour that is actually quite resistant to the light. So this time we're going to start the test off with D8 again. B4 is only a few steps away from B1. So how hard can it be to reduce the speed and increase the power to gradually push us back towards B1? There's our starting orangey gold again. We will now increase the effective heating effect by pulling the speed down from 800, let's just go down to 780. A very small step. Well, we've had no significant effect at the moment by pulling the speed down very slightly. Let's go with a significant jump in speed. Maybe let's go down to 750. So there we go. Maybe we've pulled it slightly towards a rose gold or a slight pink. Let's try 700. Yeah, we're getting a little bit of pinkiness in there. Let's go down to 600. Aha! Now we're making a little bit of progress. That's a big jump, but we've got a slightly darker pink now. It's very difficult, but as you can see in this light, have I gone too far? It's got more blue in it. Perhaps I should go backwards and check whether or not I could get a good match. It's very difficult to see in these lights, isn't it? I think we'll go and look outside in the daylight. It is so difficult to compare them, isn't it? Because you've got to catch them in just the right light. So we've got a pretty reasonable match there with our speed. So that's 650. That's gone a long way down from 800 to heat the job up. Now the question is, what's the texture of that and what's the texture of that? And in this normal light, we've got a reasonable match. Looks as though we might have a reasonable match here as well. Well, I think as well as kids and animals, we must almost add colours to the things that you shouldn't do live on camera. To the eye, they look a pretty good match. What do they look like under the microscope? At the end of the day, you're not interested in what's under the microscope. What you're really interested in is what the eye can perceive. Now over here on this screen, we can see a live view of one of the colours. Now, as you can clearly see on here, we've got some stripes. And those stripes, you would immediately think, that's the pitch, the vertical pitch at which the scan lines are taking place. No. The scan lines are taking place at 2.6 micron intervals. Here, when I measure it with my scale, this is 110 microns. There's no relationship between the pitch that I'm setting on the machine and the pitch of this pattern. Now over here on each one of my thumbnails at 50 times magnification, we can see exactly the same pattern. They're all 26 micron pitch, but they've all got roughly 110, 100 micron pitch between their stripy patterns. So here's some paper printouts of what you've just seen. These are 400 times magnification of the surfaces, and on each one of these surfaces we can see the yellow, which is the basic surface as far as I'm aware, and I've focused in on the yellow to try and get some resolution to the yellow. The blues are well out of focus on each one of these, so this is not a real D-grade colour. Although it might perform like one, it's not a real D-grade colour because we've obviously got depth, and you can't have depth in something that's only a few nanometers thick. This is probably a micron or 2 microns depth. So we've definitely gone past the thin film side of the colour. This is the master copy, which we set up to start with, and this was our emulation by approaching it with speed. It's similar, but there's more blue in this one, a lot less blue in this one. There's more yellow in here. And this one over here, which was a power copy, has got a lot more blue in it, not as much yellow, and very little pink. So what's on the surface is not what we're seeing. Although I was disappointed that I actually got a pretty good colour match, when we look at them in detail, I'm moderately pleased that it shows that we do not get a copy of the master, by approaching it with different parameters. The parameters are acting in a different way on the surface. Well, that's only just touching the edge of mixing parameters with that little experiment. We didn't really mix them very much. We only played with 2 or 3 of them. So, but you've seen the principle, and if you're really that interested, then you can go away and start mixing and matching the parameters for yourself. But trust me, playing with colours will teach you a great deal about the parameters. And I hope that the one lesson that's come through is what sharp and soft is when you apply it to each one of these major parameters, and the effect that sharp and soft will have on the surface of your materials. Now, to finish up with, I'm just going to take a look on the screen here at, first of all, this is raw stainless steel. I'm going to take a look at something that we started the whole of this colour session off with. And here we've got some yellow. And now we're moving into a slightly darker yellow. And hey, look, we've got some crystal structures growing. Now we're moving into a darker yellow. And we've got some brown crystals growing. So the interesting question that's starting to grow in my mind now is, as we move into this colour, are those blotches some sort of leaching from the background, or are those blotches growing in the oxide film? Now we're getting into a slight red. Now we're getting into very red. And the crystal structure in the background is getting smaller and more distinct. Now, isn't that fascinating? And that's, I think, as far as the colour changes go. Oh no, we've got a slightly different texture just there. And what are we looking at? That's what you were looking at. I thought you might be interested to see how that compares with all the things that we've been trying to create on the machine over the past few sessions. Now, I couldn't do that to start with because we didn't have the services of this lovely microscope. But now we have, I thought it might be quite a nice fitting end to the project. No, not quite the end to the project. I think we'll give it one more shot because there's some quite important stuff that I think you might be interested in what I think will probably be the final colour search, because to be honest, I'm getting a bit fed up with colours. I have to say thank you very much for your patience, because although some of this stuff has been fairly interesting for me because it's a learning exercise, it's still been tedious and boring. But for you, it must be like watching paint dry. Anyway, until the next session, when I can assure you it's going to be slightly more interesting, thanks for your time. Bye till then.